The video you're about to see is a real-time recording made at a live ICRI technical session. It is important for you to realize that the remarks of the speaker do not necessarily represent the views of the International Concrete Repair Institute. This presentation is intended to refresh your memory if you attended the session and to allow you to benefit from the speaker's remarks and from the question and answer period if you were unable to attend. Now here is the introduction to the speaker for this session.
Our next speaker is Robert Gaul. Bob Gaul is the President of Construction Polymer Technologies and Vice President of Chemco Systems Incorporated. He's been active in the field of concrete repair and restoration for over 30 years. In the late 1950s, Bob supervised the development of the structural concrete bonding process of epoxy injection at the Adhesive Engineering Company, where he served as president from 1970 to 1988. From 1988 to 1990, he was technical director of special restoration systems for the Master Builders Company. Bob Gaul has published numerous articles on the uses of polymer products with concrete. He's a fellow of the American Concrete Institute, and in 1988 received the Delmar L. Bloom Award for outstanding and significant contributions to the knowledge of adhesives for concrete. Bob has served as chairman of ACI Committee 503 on adhesives for 10 years. He is also an active member of ACI 515, coatings for concrete, and ACI 548, polymers in concrete. Bob Gaul is the past president of the Northern California chapter of ICRI and is currently a national director. Bob's topic this morning, moisture-caused coating failures, facts and fiction. Bob.
Thank you, Peter, for that introduction, which is only about 2 minutes shorter than my presentation. We all know that there are far too often failures of coatings on slabs on grade. Now, most of these coatings that we're talking about, and the ones we're talking about today, are what we call impermeable or non-breathing coatings. They are usually they're 100% solids polymer systems. Now, polymer systems that are applied with solvent-based are somewhat permeable, and solvent systems that are applied as polymer systems applied as water emulsions or cement coatings, cement-based coatings, are usually what we consider breathable. So we're really not talking about the breathable and the semi-permeable coatings today. We're talking about failures of 100% solids, relatively or essentially impermeable coatings. As examples of this, we're looking here at a polyurethane coating which has been applied on top of a epoxy primer in a manufacturing plant here in the Northwest. It's a very dense coating. You'll notice the patch there, which is a failure point. It's difficult to see on this slide, but there are many small blisters and some larger blisters. When the blisters were broken and peeled away with a putty knife, we noticed that at first, this picture was taken actually a half an hour after the blister was broken. What we have is and it was totally wet on the surface. It was all one uniform color, but as time goes on, the water has evaporated so that we're seeing dry concrete in the middle, but around the edges still a bit wet. Another example of a membrane here put down on a deck, and you'll see the very many. This is 24 hours after the application. See the very many small blisters. And again, a solid membrane now put down on a deck, and 24 hours later we have a lot of blisters. Today we're going to take a look at first the mechanisms of failure and take a look at the forces that are causing these failures, the possibilities, what might be causing these failures. Discuss briefly some measuring techniques to be able to predict the problem ahead of time, and then a few suggestions on how to avoid these problems. When we find the failures, sometimes we'll just have a local failure, just a little bit, a small area, maybe 100 square feet out of 20,000 square feet. Other times it will be uniform over or generally over the entire installation. When this occurs, there must be something different. There's something either different in the moisture condition, which is causing the failure. There's something different in the concrete. Perhaps it's not, maybe one batch got too much water in the ready-mix truck, or we may have a difference in the coating itself, because most of these things are applied as a result of batch mixing, and they're proportioned in the field, they're mixed together. Perhaps they're not, something's wrong with one of the batches. So we have to look at all these possibilities when we're investigating a failure. Then we have what we call failures that we see right away. It's obvious on the job, just as the job is being completed. We'll notice that the coating is not bonded properly. Sometimes a coating will fail 6 months later, after the job is finished. We say, well, all of a sudden something happened to cause this coating to fail. However, unfortunately, we do not usually check the bond of a coating immediately after the job is finished. It could be sitting there, not very well bonded. A coating in place until something tries to disturb it will stay in place. We could have a bond strength of 1 psi, and the coating would be there, and it could be something, a condition that comes on later that dislodges this. That would not dislodge a properly bonded coating. What are the possibilities that we can see here with how water would affect these coatings? Number one, some coatings may be the water affects the chemical cure of the coating. In other words, the coating never properly cures. This can happen because some coatings are sensitive to water to the extent that one of the ingredients is absorbed out, is soluble in water and comes out, or the water itself interferes with this chemical reaction. When this happens, when you pull up the coating, it's usually a little bit sticky underneath, where you can smell an odor of one of the components. It's rather obvious when this is the case. Then we have the condition where we actually get a good cure. If you take you can peel the coating up, it comes up in sheets, it's very hard on the top, it's very hard on the bottom, it looks like it's good. But something has happened, somehow water has interfered with this adhesion. There's been enough effect of the water to prevent the very intimate contact with the concrete that is required to achieve a very good bond. Then we also have the conditions where we truly did get a good bond, but sometime later, water has in some way disturbed this bond and destroyed the bond. We're going to be looking at that next. There are three ways that water can get up to the interface. One is as a result of a hydrostatic head. The other would be by water absorption into the concrete from below, and then there's moisture vapor coming through the concrete. In the first case, this slide shows a water table where we have a head of water, and there's water underneath the base. The water is being driven up through the concrete, through the capillaries in the concrete, and the rate at which this water travels depends upon the size of the capillaries. Usually the larger, the more they are, the continuity, the larger they are, the greater the water travel is going to be. And of course, the head is a controlling factor here. We also have the possibility of not a water head, but we have a source of water underneath the slab. We have base. We have water being absorbed into the concrete up through the capillaries, and as it reaches near the surface, the water begins to evaporate into the atmosphere. So the concrete looks dry on the surface, but it's really not dry. It is really dry on the surface, but there is really water coming through continuously through the concrete. I might mention something that I should have in the beginning. Frequently, we design these concrete slabs with an impermeable membrane underneath the slab. And on the membrane, we put either rock, usually, or sand, and then pour the concrete. However, unless the impermeable membrane is totally sealed off at the extremities of the building, water can come in from the side, or as frequently happens during construction traffic, or in the pouring itself, people walking around, we puncture these membranes. So even though we have an impermeable membrane, we can have a moisture problem. So this is the second method through which the water could come through by capillary action. Usually when this, and the rate again here is controlled by the size of the capillaries. The smaller the capillaries in diameter, the greater the rise of liquid water in the concrete. But, and then the condition where if there were 100% humidity in the atmosphere, then it is conceivable that the water through the capillaries can rise to the surface because it's not going to evaporate into the 100% atmosphere. A third method here is that we have higher water vapor pressure than below the slab than we do above the slab. In other words, we don't have water down here, we have water vapor. But if the water vapor pressure here is higher than above, then by a process of diffusion, the water vapor pressures will tend to equalize. So there's a pressure involved there. Now, let's look at the forces that can be exerted by these various methods of water coming through. If we have a bond of a polymer coating to concrete, it could be anywhere, it could range anywhere from, say, 100 psi to 300 psi, depending upon the ability of that particular coating to bond to concrete. Now, a hydrostatic head, we only get a half a psi for every foot. So if we have a 20-foot head of water, which is quite a bit for a slab on grade to be experiencing, we would only have 10 psi trying to push the coating off of the concrete. The capillary forces that have been measured and reported in the literature, capillary forces in concrete with water rising, range from 15 to 22 psi. This is as high as anybody has ever measured. And the vapor pressure, if you could imagine the most bizarre combinations of temperature and humidity, you would get no more than 2 psi, actually closer to 1 psi pressure trying to push a coating off. Now, if this thing is bonded 100 to 300 psi, how can these forces push the coating off the concrete? So it's our contention that if these forces occur after the coating is cured, after the thing has developed its bond, they are not going to dislodge the coating from the concrete. However, if they exist before the coating, or while the coating is being installed, any one of them will easily prevent a good bond from being achieved. Now, this leaves us in sort of a dilemma. We say, okay, what about these installations where we have measured the bond strength immediately after the project is completed, and we've got 200 psi pull-off strength, and yet 6 months or a year or 2 years later, this thing is coming up in sheets. This has led to a lot of speculation, and there's a lot of discussion about what these mechanisms might be. There are two which are being proposed in the literature. One is osmosis, and the other is somehow salts are or salt crystals are forming near the bond line. Now, let's take a look here at what osmosis is, if we're going to understand this. Osmosis is the phenomenon by which a solvent will pass through a semi-permeable membrane from a lower concentration to a higher concentration. In other words, we have on the right side, we have a solvent, it's got something dissolved in it. In our case here, we're talking about water as the solvent and salts are the solute. So there's a higher concentration, say, of salts on this side than there is on this side. And the definition of semi-permeable is that it lets the solvent through, but it will not let the solute through. So as a result, we develop a head here. And this pressure, what's called osmotic pressure, is the pressure that is required to stop this action. In other words, I think that it all reaches a equilibrium. Now, when we go to concrete, it's pretty difficult to understand what people are talking about with osmosis. There's two concepts. What we've done here is we've put an impermeable coating on top of the concrete slab. And what some are saying is that there are salts near the surface that have been brought there during the curing process. As the water is evaporating from the concrete, they're drawing salts from the concrete, so there's a higher concentration of salts near the surface than there is near the bottom, and somehow then the water is coming up to the surface. But the whole thing falls apart because water is not a concrete is not a semi-permeable membrane. It's permeable. So what we have is if the salts got up there through the capillaries, they can come back down through the capillaries. If there's anything happening here, it's a diffusion process, and if this were saturated, then the salts would be going the other way. Getting back to this osmosis for a minute, these osmotic pressures, some of the literature has taken an equation, Van't Hoff's equation, which is the old PV equals RT gas equation, because osmotic pressure is supposed to, at very low concentrations, behave according to this equation. However, what they're doing is they're assuming that the membrane is truly semi-permeable, will not let any solute through at all, and in fact, in the real world, there aren't such membranes, so that there's a big dilution factor, so you never can get. What they've done is they've taken this formula and they've predicted pressures based on this equation, but nobody's ever measured these things. As a matter of fact, there's one reference in the literature to someone measuring the pressure inside blisters on a coating, which they claim came from osmotic pressure, and they got 6 psi. So our point is that we don't believe it, that it's osmotic pressure, but even if it is, it's very low. The other explanation for osmotic pressure is that there are salts up here and that the coating itself is the semi-permeable membrane. And this would require for there to be a solution down here, which may exist, water and salts, and a solution up here of water. So unless there's liquid water on the surface, it would be very difficult for any kind of osmotic pressure to exist. But even if we don't really believe this is osmotic pressure, but again, even if it were, nobody's ever measured anything which they claim to be osmotic pressure greater than 6 psi, which again is not enough to push these coatings off. Also, if this were the case where the coating were the osmotic, developed this osmotic pressure, the liquid in here where the pressure is building up is free to go back down through these capillaries. There's a path to relieve that pressure. The other concept which is that somehow salts are being carried to the surface and the salt crystals are growing and they're breaking the bond. However, for the salts to be carried to the surface, there has to be water transfer. There has to be water coming up, as if there were no coating on the top, then we could be carrying salts up, which as the water leaves, the salts are deposited near the surface. But that doesn't happen because we have an impermeable coating. There's no evaporation. So all the water would do would be to dissolve the salts. So now, where does that leave us? There is another explanation. This is work done on water absorption of some epoxy systems, all for the same application. And you'll notice that this water absorption was taken over a 100-day period. And you'll notice here's a 0.5% water absorption. And the significance of this is that most water absorption tests that are done by manufacturers and that are published are either a 1-hour water absorption, a 2-hour water boil, a 24-hour water absorption, and they report, and as a matter of fact, the C881, ASTM C881 has a water absorption criteria, which is a 0.5% after a 24-hour water soak. But what's really happening to these systems is that after a long period of time, I mean, they take on a lot of water at first, and it tends to even out. Some of them don't. Some just keep absorbing water. And some are better than others, which can explain why some coatings do better under these conditions than other coatings. What happens when the coating absorbs the water at the bond line is that the coating swells. And these forces are extremely high, can be very high, and can break the bond quite easily. This is not only well known for concrete bonding to concrete, but bonding to other materials as well. So this is our explanation for what may be happening on these conditions where a bond breaks after a long period of time. We know, so this is all very fine, but we still have the problem. We got to get these coatings down. What do we do? Well, we know that just looking at a dry surface on the concrete is not enough. We also know that the testing with moisture testers, with the conductance tests, really don't tell you what's happening, where the water is what's going to happen after you put the coating on top. So we have a couple of tests. The first is a simple test, which I'm sure many of you are familiar with, where you tape down a sheet of polyethylene, keep it there for at least overnight, maybe 24 hours, come back and look underneath, and if it's collected moisture, what we have is moisture coming up through that slab. And if you have a condition like this, you're alerted that there is a potential problem, and you better take special care in trying to put a coating on this slab. There's a quantitative test, which is developed by the Rubber Tile Manufacturers Association. And this is a very effective and easy test. You can buy these kits. There's a desiccant, there's a desiccant here, and there's a plastic cover, and you pre-weigh the desiccant, put it in the underneath, seal it, seal all around, and put this down for, I believe the criteria is 60 hours. Then they calculate backwards a rate of water vapor transmission in terms of pounds per 1,000 square feet per 24-hour period. And the tile manufacturers use the criteria of 3 pounds per 24 hours per 1,000 square feet. And if it's below 3 pounds, it's safe to go ahead, and if it's above 3 pounds, you better watch out. We've used this with polymer coatings on concrete slabs, this criteria, with pretty good success. As long as we've stayed below 3 pounds, we have not had problems. What can we do about it? Well, the first thing is you'd use a breathable coating if you could, but you can't. A lot of times you can't use a breathable coating because you're looking for chemical resistance or ease of cleaning, and breathable coatings, if they breathe one way, they breathe the other way too. So things can go through them. So that's sometimes that's out. Second thing is what we would say, I say turn off the air conditioning. In other words, do not reduce the water vapor pressure in the building. Say it's in the building, which it usually is. Don't reduce it. Frequently we're in the wintertime and we want to put a coating down, and the contractor says, gee, it's 40 degrees, and I don't want to put it down at 40 degrees. You get too many bubbles and it doesn't handle nicely. So we close the doors, turn on the heat, turn on the air conditioning, reduce the humidity, and we're increasing the water vapor pressure differential from beneath the slab and above, which is going to cause a higher rate of water vapor transfer, which is going to interfere with achieving a good bond in the first place. Now, there are some manufacturers that recommend that the moisture vapor tests be done when the conditions are the same as they are during actual service. But if the water vapor pressure is going to be a problem during the installation, it's not going to be a problem after the installation. Stay out of the sun. What we mean here is if the temperature of the slab is rising, say if you're in a building and you have sunshine coming through a window and you've put down a coating, you're putting down a coating, if there's any moisture in that slab, the sun getting warm is going to accelerate this thing wanting to come out. So those earlier slides that I showed of that black coating and the preformed membrane on that deck were a result of this material being installed about noontime and the sun coming out and really raising the temperature, causing moisture vapor to make those bubbles. Another thing, if it takes time for these things to happen, so if you use a very fast setting primer, you can sometimes achieve a bond before the moisture actually reaches the bond line and causes a problem. And the last technique is one where we've had some pretty good success of using what we call semi-permeable membranes to reduce the rate of moisture vapor transmission. Say if you you make your test and you find that you've got 6 or 7 pounds coming up at a rate of 6 or 7 pounds and you wanted to get that below 3, you would put down a semi-permeable membrane which would reduce this rate and then to below the 3 pounds, and then be able to achieve a good bond. So that's our views on the facts and myths of water vapor or caused failures of slabs on grade. We think that there is a rational explanation for what's going on, and we think there are steps that you can take to get a good installation. Thank you. Any questions? Yes, sir?
Selling semi-permeable membrane, what type of product would that be?
Semi-permeable membrane. They're usually latex-modified cementitious coatings.
Wouldn't that present a problem in itself as far as installing one of those systems properly, getting a good bond with those?
Everything done right, surface preparation right, no extreme moisture conditions. I mean, not a totally wet slab or those materials will achieve a bond which is certainly adequate for a coating application. Yes, sir.
Water tolerant coatings for that application. Have you used those that have had success?
Moisture tolerant coatings?
Yes. Actually, use the dampness for curing rather than just bonding.
Yeah, you're talking about, now you're talking about urethane coatings which are moisture cured?
Yes.
Yeah, if you still have the same problem, I mean, there may not be an interfere with a chemical interference, but if there's enough pressure coming up, it can disturb the intimate contact that's required even for those materials so that you don't achieve a good bond. Or so it's, it depends on the degree of the problem. Yes, sir.
How do you explain, based on your theory, that a lot of coatings have the same failures, blisters, even above grade or inside, where there is no waters actually underneath the slab?
Well, there's moisture in the slab, and you don't, in those cases, most likely, our explanation is that most likely you never did get a very good bond. So it's the moisture when say, sun comes and the moisture that's in the slab wants to get out, it's going to push out at the point where the bond was the weakest.
Just like to make a comment. the ability of an epoxy coating to absorb some water in small amounts is actually beneficial to the bond line, especially when the swelling actually releases the bond stresses caused due to shrinkage of epoxies. So to the extent that you have a limited, very small amount of absorption of the water by the epoxy, is in fact in many studies they found that it's kind of beneficial to the bond line, improving the stresses of the bond line. Just a comment.
Okay.